In today's lecture number 13, we will review again the derivatives obtained via operator notation. Then we will discuss about why we need upwinding, or why do we need numerical dissipation even when we are solving differential equations which are non-dissipative in nature. While talking about upwinding, we specifically bring in the concept of higher order upwinding, because in many physical systems we have dissipative effects which are represented by second order derivative term. So, to avoid interfering with the physical nature of the problem, we need to bring in higher order upwinding. That means, we will be adding numerical dissipation which are proportional to fourth or other higher even derivative terms. This is the essence of upwinding, and we will see that this is central to many existing methodologies. So far, we have been talking about discretization on uniform grid, uniform grid of points. Today, we will just introduce you to the topic of discretization on non-uniform grid. We will focus our attention only upon first and second derivatives. Once we set this stage for the discretization, we need to be able to analyze the effect of such discretization, and one of the method that will be central to this course is what we call as the spectral analysis. Means, we instead of studying the problem in the physical plane, we will be studying the problem in the wave number frequency plane or k omega plane. So, that is the essence of spectral analysis, and the moment we fix our spatial discretization, temporal discretization and the grid spacing, we will see that we do not have unlimited resolution, and in this context we bring in the concept of Nyquist criteria that relates the grid spacing with the maximum number of wave number that can be resolved by the use of this grid. Okay. Having defined the Nyquist criteria, we basically try to show various effects of discretization in the k space or the wave number space. With that, we will conclude today's lecture. Okay, then we shall begin. If you note here that what you have here is basically a expression for the first derivative in terms of central difference operators based on half point delta or the integral points delta 1, and you can decide to stop at any point and get expressions of any order. That is one way of doing it. There is a other simpler way of doing it. That is what I demonstrated to you in the last class, that suppose say we are interested in finding out a sixth order representation of the first derivative, then we can club the terms in this particular manner. Okay. So, this particular clubbing of terms ensures that all the even derivative terms disappear, leaving behind only the odd derivative terms, and then in this equation if you equate the coefficients, that helps you generate relations for this unknown constants a, b and c. So, we are done that here, collecting coefficients of first, third and fifth derivative, and upon solving those three equations, you get an expression of this kind. As expected that it is a central representation. So, you have basically 7 points, although the middle point ith point would be missing here, right. That is the way we have constructed it there. So, same way if you decide to figure out what the fourth order symmetric stencil would be for first derivative, then you just keep this first two terms and then again go through that same process, equate the coefficients of first and third derivative, solve for it, and you get this. Now, I think this is where we were making some point that at times we need to obtain expressions for even ordered derivatives. Even ordered derivatives, like for example, here we have written down the expression for a sixth derivative. Okay. And because we are interested in even derivative, the clubbing of individual terms appears with the intervening plus sign between the pairs, and you also have d times f I, right, and go through that same exercise represented by Taylor series and compare coefficients. For example, the function on the right hand side will have coefficients of this kind, on the left hand side there are none. The second derivative on the left hand side there is none, fourth you have nothing, sixth you have 1, and then again equating the sixth derivative coefficient would give you this. So, once again you have 4 equations for 4 unknowns A, B and C and D, that will give you this stencil. Now, the question is why are we doing this, and that is where we actually stopped. I mentioned to you that in many physical applications of scientific computing, you would have equations of this kind. So, the substantive derivative would be given by the diffusion term and plus additional terms, which we are not talking about. So, what happens is this term itself you would be able to write it in a local acceleration form, and of course, the convective acceleration form of this kind. So, that is what you notice, that you need to really obtain expressions for first derivative in discretizing this equation. They would come from here, right. Now, what happens is, if you remember that when we were solving this simple model equation, then depending upon your discretization strategy for this, assume that this is exact. So, you do not make any error in discretization. So, let us make that assumption, and then you start noticing that depending on whatever stencil that you would be choosing for this first derivative, you would have methods which would be neutrally stable. I mean, the solution will behave properly as you expect it to be. And in the context, we had some discussion in a lecture a couple of days ago, where we talked about that if I do it by first order upwinding kind of a forward difference or backward difference, I actually add dissipation, and that solution would attenuate, and that is something which we do not like. And then we also said that if we do some kind of a second order central differencing scheme for this, we notice that this gives rise to dispersion. We discussed it, right. We made that observation. Now, what happens is, the moment I withdraw this assumption that we can have temporal discretization exact, we do some kind of let us say represent it like this, u n plus 1 at say ith point and u n at the ith point, and if I do it like this, this is what was our Euler method. So, we did talk about that when we were solving initial value problem, you recall that exercise. If I write this like this, we said that it will not attenuate the solution, but it will disperse, but this combination of this kind of temporal discretization with the spatial discretization makes this method unusable. If you try to solve it, you would see that this solution will blow up in time. So, this is not a very useful combination of method. We will discuss it very shortly. So, what happens? That means the amplitude will keep growing with time. So, if I want to moderate that growth in time, what I could do is I could attenuate that growing solution and try to get a balance that what I am getting numerically. Numerically, I am getting this solution to amplify, and now if I add numerical dissipation, I will attenuate with a judicious choice of the two. I could nullify the effect of one by the other, so that whatever I am looking for, I am going to get that, right. So, that is one way. So, of course, this is unstable. So, suppose if I do this, again let us say I am doing Euler time discretization, but if I do it like this, how should I do? The solution is going from left to right, right. If C is positive, that is what it is. So, what I should be doing here? I should be discretizing it such that the information will propagate from left to right. So, that would be like u I minus 1 by delta x. This we agreed. If I did that, I will leave it as an exercise for you to show me that this one would actually amount to doing this some coefficient alpha . So, what we are essentially saying that look at this, first order upwinding is equivalent to doing a second order stencil plus adding a numerical dissipation term. So, this is not there. So, this is what I will call it as numerical dissipation, right. In fact, most of computing activities relate to suitably designing numerical dissipation to do your job. That is what we would see as we go along. Now, this is perfectly okay, because we know that this solution by itself was unstable. So, the moment I added this numerical dissipation term, I am bringing into play the possibility that the amplification on this side will be balanced by attenuation on this side. So, this may work, this may work. I will have to be very careful in choosing this constant alpha. We should be able to do that, it is possible. There are many other ways of doing it. So, that is a panacea for taking an unstable method like this and making it work. This is quite often done. That is probably not a very difficult task to perform. However, suppose instead of this equation, I have been asked to solve an equation of this kind. Let us say this is some nu times this. So, this is what is called as a while that is called the convection equation. So, this is called the convection diffusion equation. So, this is a diffusion operator appearing here. Now, what happens is, if you are asked to solve this equation, if you again adopt the same kind of a thing, Euler time integration here, let us say this is I decide to do first order upwinding, okay. Then what happens is, if I do the first order upwinding, so that would be equivalent to this, that will be a second order quantity, and on the right hand side I have this term, this is physical term, to that I am going to add this term. Right. So, this is physical and this is numerical. So, this is exactly like what we are looking at here. If I decide to do some kind of a upwinding of this convection term of first order, then that would be equivalent to adding some second derivative term like here, alpha times this, right. So, what happens then? You are in a dilemma, because to numerically stabilize what you are doing, you have a physical term, to that you are adding a numerical term. This numerical dissipation added actually interferes with the physical dissipation, and this is dangerous, right. So, what one can do is, instead of going through this route, will not do this exercise. Suppose I do it like this. So, I have the physical dissipation term, and the numerical dissipation, instead of adding with second derivative, I will add it with, let us say, some even higher order derivative, right. So, then what will happen? This is still a dissipative term, but it is not going to interfere with the physical dissipation. So, this is what we call as higher order upwinding. Please keep in mind that there are practically no computing methods which do not use higher order upwinding, or the concept of upwinding is all pervading. You cannot avoid this. If we do not do upwinding, we end up getting numerical instability. So, upwinding is the order of the day, you have to do it, but the question is how do you do it? Would you do it in a lower order fashion like this, or a higher order fashion? Lower order means where the numerical dissipation is proportional to the second derivative. Higher order means it is higher than second. It could be fourth derivative, it could be sixth derivative. Those of you who may have heard people talk about spectral method, which is supposed to be the most accurate numerical method of computing. Even in spectral calculations, people do add such terms, and of course, they give a very fanciful name. They call it as hyperviscosity term. So, if this is your viscosity type of term, so since you are doing it with a higher order derivative, you call it a hyperviscosity term. So, it's something you got to get used to the idea that there are no computing methods which will perhaps work without some bit of upwinding. So, that's something that we want to do. And what is the way you do upwinding? You have seen that when I do first order upwinding like here, that is equivalent to discretizing the convection term by the second order plus a second derivative term. So, that is your first order upwinding. So, I can extend this logic. Suppose I do not write it by second order central difference scheme, but I want to do it with this, a fourth order term here. Yeah. So, we have a fourth order fourth order accurate representation of the convection term, and again you will notice that keeping it as a Euler time discretization with fourth order central differencing of the kind given by that equation 36 will still make the method unstable, right, will still have an unstable method. So, you would have to add some kind of a dissipation. So, I would make the point that in most of the computing you do not like to add second derivative term, because the physical dissipations always appears with the Laplacian operator, and that is the second derivative, right. So, we do not like to give a second derivative term, instead we would like to have a fourth derivative term. So, if I have a fourth order representation of the convection term and on the right hand side I add a equivalent fourth derivative term, that method will be called as third order upwinding. Okay. So, this is a nomenclature and you understand the logic. So, if I talk about nth order upwinding, I am talking about n plus 1th order central differencing plus a derivative which is n plus 1th derivative. That is what we have been doing. See, we have first derived this 6th order accurate and 4th order accurate expressions for the first derivative, and now if I want to add a 5th order upwinding. So, what I would be doing? I will take that 6th order central difference scheme for the diffusion term, the convection term, to that I will add this 6th derivative term. And if I want to do third order upwinding, then I will do with a CD4 or central differencing scheme of 4th order for the convection term, and I will add a 4th derivative term as a numerical dissipation. So, that is the whole idea that suggested to us that we follow this. Yes, any question? Please tell me. You have a question? Do not feel shy. I mean, if you have any confusion, let us discuss it. Well, if he does not, then we will carry on. So, this is a very standard fare. For example, quite a few of you may have even used some of those commercial software, like that the Fluent is one of the one that is quite often used. In Fluent software, what you would find that it has options for you. Either you can do it by first order upwinding, that is the basic menu. If you do not suggest anything, without your knowledge it will do first order upwinding. And then you understand what it does, that added numerical dissipation actually interferes with the physical dissipation, and the results are of course suspect most of the time. However, if you go back and now look at the code, Fluent code, you will notice that they also give you an option that is to do with third order upwinding case. So, that is equivalent to what I just now explained to you, right. So, this is just for you to get familiar with how these things are done. So, here we have shown you how a 6th derivative term is obtained, so that we can construct a 5th order upwind scheme, or we can obtain a 4th derivative term, that would be this. So, to this if we blend that 4th order central differencing scheme, then we can generate the third order upwind scheme. Okay, so this is what we did. Now, so far we have been talking about all these expressions that we have had so far, where with a grid with the grid points are spaced equidistantly. However, in most of the calculations that you would notice, like the assignment that you are doing, if you have a boundary layer very close to the wall, then you need to have very fine spacing near the wall. It would not be very smart to continue with that kind of discretization for the whole domain. That would amount to taking astronomically high number of points. So, what one ends up doing is basically take points which are non-uniformly distributed. So, wherever you have gradients, flow gradients, that is where you have finer spacing. As you go away to regions of interest, where the gradients are not so large, you can keep on increasing. So, if we do this, how do we obtain the derivatives? I have just given a very simple example. Let us say we have a function of x, that is y, is distributed over non-uniform point. So, I have a spacing about this central point x I, which I call as h L to the left, h R to the right. Okay. So, now what happens, I could obtain this value from this value by this Taylor series, right. So, x I plus h R should be written as y obtained at x I plus y prime into h R, and so on and so forth. So, you have a couple of expressions for the function to the right and to the left here, right. So, one can basically use these informations, Taylor series information, and obtain derivatives. For example, if I decide to write the ratio of this grid spacing h r by h l as some quantity called beta, then the right hand neighbor can be written down in terms of this, right. So, that is quite understood. So, what we have done, instead of writing h r, I have written beta into h l, right. There is nothing, simple, as simple as that, and then this left neighbor has been written in terms of h l. So, we have tried to write everything in terms of h l, and this grid parameter, the ratio beta. So, if I look at these two expressions and perform this combination, so I basically, so this left hand side is nothing but y I minus 1. So, if I multiply by beta square and subtract from there, then of course, you can see the second derivative term will go away, and I will have the function itself minus beta into beta square into y I, then the first derivative will remain, right. So, first derivative remains like this, and the next higher order term will be proportional to h l cube, right. So, what I could do is I could simplify it, and from this I could obtain the first derivative in terms of this. So, since I have divided the both sides by h l, so the leading truncation error term is proportional to h l square. So, by the classical sense, you will be talking about it as a kind of a second order accurate, as well as in terms of a polynomial series, that also is a second order accurate representation. So, this is an expression for the first derivative. We can similarly manipulate those two equations by multiplying the second equation with beta cube, and we can add it to the first equation, then we will get an expression of this kind. By performing this, what we have done is we have obtained an expression which involves everything, including y prime at x I, but you know already we have expressions for this quantity. So, we can use that, and when we use that, this is what we get. Okay. So, basically this is what we are getting, and this is an expression, again a second order accurate expression. Okay. So, this is something that I think we spent more than that is adequate for discretization. We will come back to it when we go to different thing. Now, let us start off with a lecture, or maybe it will spill over to the next one. We talk about analyzing computing methods, and this was essentially been developed by a few groups including us, and this actually refers to expressing the quantities in the k and omega plane, wave number, circular frequency plane. And that was one of the reasons I spent a disproportionate amount of time in familiarizing you with the waves. So, this is the reason, and let us see how we go about doing this. And as I have been telling you, this is our favorite equation, because this has special property. The property is that the solution is non-dissipative and the solution is non-dispersive, and this is we are talking about the analytical or the exact solution behavior, right. Now, what we like to do is represent the solution in a discrete plane, right. So, the points are at discrete x locations, which I have indicated by u of x m, and let us say we are defining the solutions at discrete times, which I have indicated by t superscript n. This will be written like this: u subscript n superscript n. So, the subscript refers to space, superscript refers to time, and then what I would be doing, I would be writing that quantity in the k plane. Okay. This is your Fourier transform, right. So, what is it? The Fourier amplitude, Fourier Laplace amplitude, that will be a function of k. The time dependence I am putting it in here. So, this is like your t to the t n, and x variation we write in terms of k integral, right. Now, same way we can define the initial condition that would be given in solving equation 1. So, initial condition is defined as n equal to 0, and that would be defined by the spectrum at t equal to 0. Whatever initial condition I give, I can do a Fourier transform, and the quantity I will write it as u naught of k, right, and that is distributed in the k plane. So, that is what we get. Now, the next thing that we want to do is try to understand when we compute what we want to do. If you look at equation 3, I have been silent on limit of integration. Ideally speaking, one would like to basically extend the limit from minus infinity to plus infinity. You take all possible wave numbers. A priori, I do not know what the initial condition is. So, that is there. So, in writing 3, we did not put any lower limit or an upper limit, but the moment we decide to work on a finite grid, then what happens? This is something that I would like you to pay attention to. Think of the following, that we have let us say for ease of understanding, we will talk about uniform spacing. So, I will write down, and let us say this is my initial condition, which I will write it as a function of x. It could be something like this. Okay. So, what I would be doing, I would be let us say dividing this domain into equispace points. So, delta x, let me just define it as h. Now, if I work on such a grid, what is the smallest wavelength wave I can describe on that grid? What should be the smallest wavelength wave I can describe? Two pi by delta. Yeah. So, what we are saying that if I want to adequately describe a wave, so let us say this is the wave. So, how do I define a wave? Let us say the amplitude, then I define its phase, and it could have also a phase shift. So, how many quantities are there? 3, right. So, I need to obtain A, I need to obtain K, I need to obtain phi. So, if I were to fix these 3 quantities, I should be able to substitute it at 3 distinct points, independent points, and then I have 3 equations, 3 unknowns, I solve it and I know everything about them. So, what happens is you can very clearly see that with this kind of a grid, I really can describe the smallest wave that is equal to 2h, right. These are those 3 points that I could think of, because if I try to do it like this, I do not have a complete description of the wave. The wave is not completely described. So, basically to describe a complete wave, I would require the full wavelength to be spread over 2h. So, that is your lambda minimum. Lambda minimum is 2h. So, what I will get? The corresponding k would be the maximum. K max would be what? The number of waves in length 2 pi, right. So, I will write 2 pi by lambda min. This is the definition of wave number. So, what I get is pi by h. So, having picked up a grid, a discretization which is characterized by spacing h, I immediately can say that the maximum wave number that I can resolve is this. This is what is called as the Nyquist limit. I think most of you are familiar with it. You must have heard of it in your electrical engineering course, right. If you sample a data at an interval of delta t, you immediately say what is the maximum frequency you can resolve, and that frequency you call that as a Nyquist frequency. So, it is the same thing. So, you understand the logic is exactly same. So, what happens then? The very fact that we are constrained to work on a grid of size h tells us that despite our fervent wish that we should like to take it from minus infinity to plus infinity, all we could do is we could go from minus k max to plus k max, right. So, this is the first lesson that you understand, that in performing discrete computing, your ability to resolve a function is limited by the choice of the grid that you have made. Okay. So, that is your Nyquist limit. Now, I suppose after this you should not have any confusion about this. What happens then? If I am trying to evaluate a derivative, what do I do? We have seen now, we have written quite a few, including today, that if I want to do it by second order central scheme or a fourth order or a sixth order, what I end up doing, I get the derivative in terms of a matrix operation, a C matrix operating on the U array, right. That is how we pick up the points. So, if I do that, I can symbolically write it in a linear algebraic form in this fashion. So, we do not want to go into the nitty gritty of x method versus y method. Let us keep it as general as possible. We talk about a C matrix, you choose your C matrix and you do the analysis, that is your part of the deal. Now, what happens is, if I represent a function like what we have written there, if I write it like this, well, I would prefer to write, allow me to write it in complex notation. This makes life much easier. So, we understand that we take the real part of that expression, right, and that is where writing in the complex form also is necessary. Why? Then you can explain phase shift. See, if I excite a system at a wave number k, the response need not necessarily be following with the input, the output could be phase shifted. That is what we wrote, remember, k x plus phi. So, that phi comes from here. I will have a real part plus imaginary part, and then we can explain that. Now, if I write it like this in the spectral form, now if I take a derivative with respect to x, what do I get? Well, I will get this. So, taking a derivative is rather simple. What you do? You take the Fourier Laplace amplitude A multiplied by the corresponding I k and perform that integral. There is a very specific name to that integral. Those of you who are from maths, you may have heard it, you may not have heard it. It is called a Bramowitz integral. Okay? So, we will not talk about it any more than that, but do understand that in performing the Bramowitz integral, I will take the Fourier Laplace amplitude and multiply by individual I k, and I get this. So, this is my exact representation, is not it? However, when I am going to do it numerically, then what happens? I do not get that. So, what do we get? Let me just demonstrate that to you via an example. Let us say we decide to show you the derivative at the mth point in terms of, let us say, the CD2 formula that we have been talking about. Okay. Now, of course, n is implied here, so you can write n. So, I have no quarrel with that. What happens is, we have already written this as u of k of T n e to the power I k x m dk, right. So, what do I get from here? So, this is at x m and T n, write this 1 over 2 h. What about this quantity m plus 1? M plus 1 means I k x m plus h, is not it? So, I would write this, the integral remains, u remains the same for all the methods, and here I will write this as e to the power I k x m plus h, that is this part, and this part will give me e to the power I k x m minus h. Okay? And this will be performing that, right. So, that is what we get. So, what happens here? I could see that it is 1 over 2 h. I will do this, I will keep the u here. What about this? E to the power I k x m is same. So, I have e to the power I k h minus e to the power minus I k h, right. So, I have e to the power I k h minus e to the power minus I k h, and then I have e to the power I k x m d k, and this. So, what we are getting then, I will write this, because we have taken a second order central scheme, I will get that. What is this? This is 2 I sin k h, right? So, we are getting it. So, I can cancel the 2 outside. So, I could write it like this, u, which is of course a function of k and T n, and then I have what? I sin k h, and there is this h there in the downstairs, and this is multiplied by e to the power I k x m d k. So, if you now compare this expression with the so called exact expression that I just now deleted, it is in your notebook. What you notice that in the exact case, what you did? You took the Fourier amplitude, Fourier Laplace amplitude, and multiplied by I k. But here discrete operation forced you to do not by I k, but some kind of an equivalent quantity, right. This I k equivalent is basically this. Or I could knock off this. What I could write here is k equivalent by k would be equal to so. Now, that is what you are seeing in equation 6, that what I said, that when I am doing some kind of a discrete operation, then of course, I have to sacrifice. I can't have I k, but I will have I k equivalent. If I were doing spectral method, that k equivalent is k. You know, spectral method means you represent the function in terms of let us say some orthogonal basis, like the trigonometric function here. So, that itself will give you k equivalent should be equal to k itself. Now, what about this? If you look at this expression, what you have? So, if I am looking at the derivative at the mth node, what is it that I should look at on the right hand side? I should look at the mth row of C matrix multiplying the whole vector u, right. All of you see that? What does the right hand side represent? This will be nothing but various rows operating on the u vector. So, if you do that, on the left hand side information is for the mth node, whereas on the right hand side u's are all the u's. So, u1 to u capital N. What I am suggesting to you, that if I am looking at the say jth node, then what I should be doing is basically project all the different points that we have, say x l which I am writing. So, basically look at this, this is integrated for all the nodes L equal to 1 to capital N. So, I have those expressed in terms of I k x l. So, what I am trying to do is I will try to project all those x k l into x j. So, basically I would take the entries of the C matrix, which I will call it as, so this is a jth row for all possible L, and this is a kind of a projection operator that would project every point into the jth point. So, for example, if I take x 1, I will multiply by e to the power I k x 1 minus x j into e to the power I k x j, right. It is just a simple sleight of hand. So, there is not much about it. So, what I find that we have been able to really get these information of what this k equivalent is at different point in terms of the C matrix and this projection operator. So, this is a nice way of looking at the information in a matrix form. So, it actually allows you to take a look at the k equivalent at all the points. Why we are talking about all the points? This is something you must realize that this del u del x, the equation 5 that I have written, that will have different type of formula for different point. For example, say if you are trying to obtain the derivative in terms of the fourth central representation, that you can do it only from the third point onwards, because you realize that you need 5 points, right. If I try to do it at second point, I go outside the domain, or if I try to do it at n minus 1, I again go outside the domain on the right hand side. So, what will happen? The entries of C may not be homogeneous for all the lines. It will depend on how you have tackled different points given the circumstances, right. So, what happens is the C matrix that we are writing here has all the information about what you do in the middle or what you do at the boundary. So, all that information is built in there in C matrix, right, and with the help of that you can actually obtain this k equivalent for different nodes. So, this is something you can take advantage of, you can find out how these things are doing. So, if I for the time being I look at second order central differencing, I have derived it for you here, what that k equivalent is. Because it is a CD2 method, so I just simply added a superscript inside the bracket to indicate it is a second order form, and that is sin k h by h. Now, we have written down those expressions for the fourth order accurate derivative for the first derivative, and you simplify the way we have done it. So, what you would be doing? You would be writing the stencil in terms of all those points, right. That would have m plus 2 to m minus 2, and you could go through all this. You will have some of this kind of combinations. Those combinations will simplify and give you this expression that I have written in the end. And since it is a fourth order representation, so we indicate it by a 4 in the parenthesis. That would be nothing but sin k h by h into this factor. So, what does it mean actually? It means the following. On this side I will plot k h, okay, and on this side I will plot, let us say, k equivalent by k. Why I am doing it? Because this is the best way of representing it in a non-dimensional form. K has a dimension of 1 over length, k times h would be dimensionless. And what is the k max? K max is pi by h. So, k h will go from 0 to pi. So, right. So, this pi is your Nyquist limit. So, this is a universal description of the thing. Now, what about k equivalent by k? Ideally, what I want it? Ideally, I want it to be equal to 1. I do not want any loss of information. But what happens? What is this? This is less than 1. So, what you are going to find that this goes like this. Well, you do not need to plot anything on the other side. If I would have plotted on the other side, what would have happened? It would have done like this. You recall? You may have done it in your Fourier transform course. This is what you get. So, this is your and ideally it should have been equal to 1. So, what is happening? That in performing discretization, what I am losing out is this much of information at every k. Ideally, I should have been there, but I am here, and my loss of information is more at higher wave number than at lower wave number, right. So, you see discrete computing brings its baggage of loss of accuracy, and this is what you are seeing, the effectiveness of the first derivative itself. What about k equivalent 4? If I plot it, it would again, you can see it will come to 0 at pi at the Nyquist limit. So, what you find that increasing the order of representation, you are actually getting higher accuracy, right. So, we have done the 6th order representation also. So, you could go ahead and you could do it like this, and you will see that might be something like this. So, these are all explicit method of representing derivatives, right. So, explicitly I am obtaining the derivative in terms of the functions. So, that is why these are called explicit methods. For explicit methods, you find out that higher the order, you get higher accuracy, right. That is what we are seeing here. We can generalize it and we can show it, right. So, if I have obtained this, and since we are trying to solve the convection equation, that derivative I have just written in terms of 1 upon h c j l e to the power I k x l minus j. So, I have basically written down the expression for the governing equation in the k plane, right. Look at this, these are all capital U, the Fourier amplitude. So, plugging the Fourier Laplace representation in equation 1, we get this. Okay. I will stop here.